Thanks, Sham, and thanks everyone for coming today for my talk. So I am Eduardo Cuervo from MSR, and I'm going to talk to you about getting really good graphics in your mobile phone through GPU offload. And this is work in collaboration with Duke University and the University of Washington. So mobile gaming is really popular today. It turns out that almost half of the mobile users play games. And when these users are interacting with their phones, they are playing games almost half the time. Unfortunately, these mobile users cannot get the high detail experience they can get on a high-end GPU or a high-end desktop on their mobile phones. And this is because, unlike desktop GPUs, mobile GPUs are heavily constrained by the physical limitations of the mobile form factor. That is, their heat dissipation is limited as well as their power consumption. And it is because of these physical fundamental limitations that we really don't expect this gap to change. Our goal with Kahawai, which by the way means streaming Hawaiian, our goal is to achieve a high-end desktop experience in your mobile device. So let's take a closer look at how a game will look differently with a powerful GPU and a low-end mobile GPU. So I guess it's really easy to tell which one is which. One is like a very bland, kind of yellowish image that you really don't want to go and play. And the other one that takes like 250 watts and you really want to go and play is the one that we want to give you. So already industry has taken a look at this problem and is doing something about it. What they are doing is a thin client solution. In a thin client solution, what happens is we have this big beefy server in the cloud that will render the game in the highest quality settings. Then the server will take these images in high quality and will send them to you as compressed video. The problem with this is that it requires a high amount of bandwidth. And this is a problem because, well, first, bandwidth is limited in many public environments, and you can run out of data in your mobile plan. And also, because if you're the cloud provider, this can be very expensive. And there is another drawback to this approach. Well, if you are not connected, you don't get to play. So, as I was mentioning before, the mobile device has a GPU that even if it's not as capable as the desktop one, is still fairly capable, and it's sitting idle there in a thin client approach. So the question is, can we use this GPU that is just sitting there to overcome the limitations of a thin client approach? And the answer is yes, we can, through GPU offload. What we are going to do is to get the mobile and the server to work together through a set of solutions that we call collaborative rendering. What we get with these solutions is basically when you're online, you will get really high detail graphics by getting the mobile and the server to work together in concert. And when you're offline, well, you will get the low-level graphics that your mobile device can give you, but hey, you can still play. But how does this solution help us to reduce bandwidth? Well, it's simple. The mobile device will render a low-quality version of the game, while the server will render a high-detail version of the game. That way, the server only needs to send the missing detail back to the client. That way, the client mobile device can show you what the server rendered. Now, for the rest of the talk, first I will introduce a few background concepts important in game development, and then I will go and introduce the two solutions that we proposed: collaborative rendering, delta encoding, and client-side iframe rendering. Later, I will mention some implementation details that are necessary for these two techniques to work, how we evaluated these techniques, and then I will close with some related work and conclusions. So, game developers don't really like to reinvent the wheel every time they build a new game. So, if you have a game, you don't want to build every time the physics engine, the audio engine, rendering, networking, AI, and so on. The game developer only wants to work on what's specific to the new game. That is the game logic, the art, assets, sound effects, music, all that. It's because of that game engines are very popular, because they can take care of all these concerns and let the game developer focus on what's important. Something else that is very important about game engines is that they provide us with what is known as the game settings screen. And if you play games, you will probably have seen this screen before. What these screens allow you to do is, if you have a cheap, low-power desktop, you can still get the game to play, even if it's a lower detail. But if you have a really beefy, high-power desktop, you can tweak everything to the maximum to get the best experience, the experience that the game developer wanted you to have. And we are going to take advantage of this feature extensively during the system. And this is because games naturally do this kind of behavior. So let's take a look at how this works in another game. This is StarCraft 2. This is StarCraft 2 in low detail. Take a look at how much better it looks in high detail. Take a look at, for example, at the floor. Look at the tiles, look at the cracks. You don't get any of that in low detail. So really, this is the kind of experience that we want to give to mobile users when they are playing, even in their phones. So, let me show you the first technique that we are working on. So, delta encoding. Delta encoding will get the client to render the frames at full frame rate, but at a low detail setting. This is Doom 3 at the lowest possible level of detail. So take a look at everything looks bland and not many details, not many carvings. At the same time, the server will render everything again at full frame rate, but using the very high detail settings. Just take a look at the comparison. Look at the door, look at the carvings missing, look at the shading, look at the guy. Everything here that looks so nice is not here. So the server will render this version, and in addition, it will render the same version that the client was doing. So we will have high and low. With these two versions, the server can do a pixel by pixel delta that will represent most of the details that we missed. Take a look at the door. All the carvings, all the shadings are there. And this delta is going to be sent as compressed video. And it turns out that these deltas compress really well. Now, for the second solution, client-side iframe rendering, let me first introduce you to what is an iframe. And for this, I will give you a very brief video compression primer. In video compression, there are two types of frames. iframes that compress more or less like what a JPEG file will compress. And p-frames that are frames that depend on previous frames in the stream. So for example, here we have a guy running towards a house. The first frame, an iframe, will encode everything in a single frame. And the second frame, a p-frame, since we already have the house that didn't change from the previous frame, we don't need to encode it again. So we just need to encode the guy. It's for this reason that p-frames are much smaller than iframes, and it's for this reason too that p-frames appear much more often than iframes on the stream. So what does this have to do with our second technique? Well, in client-side iframe rendering, what happens is that the mobile device and the server will both render the same game at the high-level settings. The difference is that the server will render all the frames and the client will only render a subset of those frames. But this is not a problem because the server will encode all the frames that are missing as p-frames and send them to the client. That way the client will get all the frames again. Something that is important is that the client frames will remain completely uncompressed and completely free of any kind of compression artifact. That will allow the p-frames to compress much more, and we will get a better overall quality or compression level. Now, to make these things work, we need to get certain implementation details right. A very important one is synchronization. So imagine we are playing a game, a Street Fighter 4, like a fighting game, in a delta encoding setting. So let's say that we do a high kick, and in the client, the guy blocked the kick. In the server, in high quality, the kick was dodged. And in low quality, hey, guess what we hit? Well, that's terrible because then we have like 3 instances that are doing a completely different thing. Unfortunately, unlike other code offload approaches, we cannot just go and synchronize the whole state of the game because it's really huge. What we really need is to make sure that for a given input, we get the same output in all the 3 instances. What we really need is what we call deterministic graphics output. And to get this deterministic graphics output, what we need is to get rid of all the sources of non-determinism, being the most important ones, the system time and the input. For the system time, really the problem is that the frames take longer to render in the client. Sometimes take the same, sometimes they take much longer. And this is a problem because let's say we see some code that is doing something like this, something like reading the system time to get a random seed. Well, in the server we may get a value of 52 if we do this in the middle of frame 4. If we do the same in the client, we are going to get a value of 62. And well, that's not good because all our values are going to diverge. What we do instead is we use a logical clock that will move forward only when a frame finishes rendering. So in this case, we have 60 frames per second, so we are going to do steps of 16 milliseconds. The first frame will have a time of 0 milliseconds during all the frame. The next one will have 16, and so on. That way, when we get the same system time, we'll get 50 in both places, and problem solved. The second problem, which is kind of a different side of the same coin, is input handling. Normally, what will happen is we sample input in the client, and because the client is, well, right there, the input can be applied immediately. Unfortunately, in the server, we need to send the input over the network, so this input will reach the server sometime later. In this case, let's say that we sample input at frame 1, and this input will be applied at frame 2 in the client and frame 3 in the server. And this will keep happening, which is not good. What we do instead is we are batching the inputs, and we are annotating these inputs with a logical clock. That way, the server will wait for its matching batch before it's processing the frame. For example, here in frame 2, we are going to send the input, and we are going to apply it in both sides at the same time. And this will happen over and over, and voila, we have deterministic graphics output. We implemented Kahawai in two very different games. The first one is Doom 3, a first-person shooter, and the second one is Street Fighter 4, which is a fighting game. Now, we wanted to make sure that Kahawai worked the way we wanted. So, from the techniques I described, it can be seen that we can just make the device work offline by disconnecting it and letting the GPU render the game locally. But how about bandwidth? How about video quality? And then, if we get that, are we negatively affecting latency? Are we making the users mad? Well, let's see about that. First, we have a graph showing bitrate against quality for one of our Doom 3 scenes in Kahawai. Here we are comparing in orange, thin client, and in gray iframe. I want you to look at this point in particular because it's a very nice result. Thin client will take about 7 megabits per second to render a slightly lower quality image than what Kahawai doing iframe can render for 1.2. So this is roughly 1/6 of the bandwidth for the same quality, which is pretty good. Now, Delta is really good at low bit rates. So if we look at Delta, we can see that we can get a video game playing at a good quality for as little as 600 kilobits per second, which again is really low. Now, what's the impact of Kahawai in latency? We can see here that running in two different configurations, 2 milliseconds and 70 milliseconds of base network latency. For your convenience, I have a green line showing these 70 milliseconds. The cost is mostly constant. So for example, it will be 20 milliseconds for a thin client. Our approach is adding a little bit more than that, 30 milliseconds. And in Delta, we have a little bit more. And actually in Delta, it's mostly because of implementation details that we can further optimize. Now, we really wanted to know, are our users happy or mad? They are happy. We picked 50 Microsoft users from different mailing lists, mostly gamers, to play the game in different configurations. And that's what we found out. So, Kahawai and Thin Client scored pretty much the same in vision quality. It's indistinguishable. And if we come to how smooth the game experience is, well, iframe and Thin Client, again, are pretty much the same result. And yeah, Delta scored 1 point less, and this is mostly because of the extra latency we added. And we can conclude that latency is very important here because the graph I'm showing here is just for the 70 milliseconds version. For the 2 milliseconds version, actually the results are much better because the latency is not kicking out that much. So really the factor to a smooth experience is not really which solution of our techniques we're using, but instead how much latency we have. I just introduced two collaborative rendering techniques. The first one, delta encoding, and the second one, client-side iframe rendering. With those two solutions, we can reduce bandwidth by as much as 6 times, or stream games for as little as 600 kilobits per second. All of this is done with a minimal impact on the user experience. Thanks.